Oh, great. Um, hey guys, welcome you all to Techceleration's Rust Talks. Today we are all gathered here to hear to Mohit Agnihotri, who's Toyota connected, who's going to present in our organization, who's going to present about concurrency in Rust. Um, and then we are having a small contest results that we conducted a contest called Code Crunch, which we have over the time we are gathering the responses from a lot of enthusiastic engineers, um, and then we are going to uh, announce the winners, and kind of the winner is going to present about the solution from the contest. And then at the end, we kind of have the big daddy of Rust for Toyota Connected, like um, Eric McBride. Eric has been a strong proponent of Rust for a long time that I have known. And Eric is here to talk about builder patterns, interop with C, FFIs, and related stuff. So excited to organize this Techceleration. So a few words about Techceleration before we get it started. Techceleration is Toyota Connected India's take on building communities around tech. So Toyota Connected India addresses the importance of building tech-driven communities because we gather a lot from the communities, we give a lot back to the communities, and we have been doing this for the good part of last year, and then we will continue to do it strong um, in the future as well. And we are also trying to constantly innovate and educate about the best practices in the industry, some of the things our people do, some of the things that we are trying to host other company people also to present with us, building a lot of collaborations. So these are a lot of agendas that we are trying to derive out of Techceleration. And this Techceleration, we have been thinking a lot about having a Rust-oriented event, like purely Rust, right from the Code Crunch contest, having our own in-house expert to give a talk, having Mohit talk about concurrency in Rust. It's a completely a Rust-flavored event, and we wanted to organize such an event because Rust is a very niche language even now, and especially in India, having Rust as one of the known programming languages for people is kind of very niche, and we are trying to make a voice in this, and we are trying to give a note to the people that hey, we are doing some cool things in Rust, and interested people can join us as well in this journey. So so this is the agenda of Techceleration, and for this event, the talk is going to get started by Mohit about concurrency is Rust, and then we are going to have a small session about Code Crunch, the contest winner, who's going to present his solution for a short amount of time. And then after that, we're going to have our Rust expert talk about builder patterns in Rust and interop in Rust. So, Mohit, over to you, man. The stage is yours.
Thank you, Srini. So, hi everyone. Today I'm going to talk about the concurrency in Rust. So, before that, let me introduce myself. I am Mohit Agnihotri, and I am the software developer and having around 6 years of experience. And I am very much passionate about IoT and embedded system. And I also founded a hardware startup after graduation. So let's deep dive into a concurrency in Rust. Before that, I want to talk about the agenda of this talk. So first, I will go through the concurrency and the associated challenges, why people think it is very hard, and then I will move to the Rust concepts, the basic concept, that is the safety, ownership, borrowing. Without it, it's very difficult to understand the actual concurrency in Rust. So I will go through it, and then I will talk about the fearless concurrency with Rust, why concurrency offer it as a fearless, and then I will talk about some implementation that is based on the library in Rust. So let's start with the basic definition of concurrency. Sometimes people got confused between the concurrency. So it is the kind of executing multiple tasks at the same time, but it is not the necessary that the task should be implemented simultaneously. Like you can also understand that we can sing or eat at the same time, but we can't do it simultaneously, right? So this is the concurrency. And there are various ways to achieve the concurrency depending on the architecture. If the architecture or environment is the single core, then we can achieve via the context switching. We can we can we can do the time slicing between the task, as you can see in the diagram one. And if the environment is multi-core, then we can achieve the concurrency via parallelism. Mostly people also confuse between concurrency versus parallelism. So in parallelism, we execute multiple tasks simultaneously over the same time period. So in the diagram 2, you can also see how we achieve the concurrency via parallelism. The main part comes when we see the concurrency implementation. So it also comes with some challenging tasks that when we try to implement the concurrency in other programming language like C or C plus Java. So it gives some problem, that is the data racing, double pre, deadlocks, use after pre, and there are many challenges that we generally face when we try to implement the concurrency. So before deep diving into the concurrency, I will give some introduction about some basic REST concept so that everyone can be on a single page. Moving to the first safety aspect of the Rust. So you generally heard about that Rust is a very safer language when we say. So what it mean by the safety in Rust? So it is kind of it is telling about that it is the same safe from the mistakes, or you can say that it is safe from the undefined behavior. So we generally see in other programming language like the condition of the data tracing, the null pointer referencing, and read of uninitialized memory, etc. So these things actually in Rust it is safer from these problems. As in the right side, you can see the example. It is written in C++, where the mutation and aliasing both are happening at the same time. So if you are not aware about the mutation, so mutation is the kind of if we want to alter or change the variable value, so it is the mutation. And the aliasing is when two or more than two variable try to access the same object or same memory location, so it is the aliasing. So now we can understand this example. In this example, we have the vector of string, and vector itself stored in the stacks, and we got the pointer, and we are transferring the data into it. And when we trying to push the data into the vector, so there may be a condition that it can, sorry. There may be a condition that vector length might be equal to the capacity. So it can it cannot initialize the value because of and we need to also allocate some new location to store the data. So in that case, there may be a problem that if we initialize the new chunk of memory and the element is already pointing to the previous memory segment. So to avoid such a situation, we want to avoid the mutation and aliasing at the same time. And in Rust, we are offering such solution that either mutation or aliasing is allowed at a time. So Rust gives the concept of ownership and borrowing. So it is the foundation pillar of the Rust. using the ownership and borrowing, we will see in some next slides that what we can achieve. So first, I will go through the ownership in Rust. So I will just talk about the what are the ownership rules, and by using these ownership rules, what we can achieve. So there are some rules. There are three rules generally, and one rule number one say that every variable is the owner of the value, and each value can only have one owner at a time. And when the owner goes out of scope, then value will also be dropped. So in the right side, you can see in the example that when we create a vector and we are trying to push the data 1 and 2, and when we call the get method, and we are actually trying to transfer the ownership to the function here. So when we trying to push the data into a main function, then it will the Rust compiler will give the error that it is already moved to the function. That's why it gives the error at the compile time. So as you can see here that actually it is transferring the ownership to the get function. So according to the ownership rules, if the owner goes out of scope, the value will also be dropped. And ownership allows only mutation but not aliasing. It is the key point. And in the borrowing concepts, borrowing is about the transferring the ownership temporarily. Like there are two type of borrowing in Rust. One is mutual borrowing that allows the mutation but not aliasing. And second is the shared borrowing. In that we only allow the aliasing but not the mutation. So in the right side example, you can also see that we are trying to initialize the string hello string, and we are trying to call the calculate length function, and we are transferring the reference of that variable, and it goes here, and it is the shared borrowing, the example of the shared borrowing. And here we are trying to print the length of the string and string itself. So it is the example of the referencing. So now we can see the benefit of ownership and borrowing. Ownership and borrowing gives so many advantages like memory safety, no data races, no runtime. In C or C++ kind of programming language, it gives the no runtime, but it does not provide the guarantee of memory safety, and it also not prevent from the data races condition. And in another language like Java or Ruby or JavaScript, it has a garbage collector. It gives the memory safety guarantee, but it is having the longer runtime, and it is also not preventing from the data races. So, but in Rust, you are getting the benefit of all the three things here. Now, I will talk about the core concept, that is the fearless concurrency with Rust. So as you see, the strong concept of the ownership and borrowing, and by leveraging the concept of ownership and the borrowing, concurrency, fearless concurrency in Rust, Rust actually give the guarantee that it is safer, it is safe, it is safer, as well as it also give the performance like the system programming language like C or C++. And it also gives the guarantee that there will be a no question about the data races, no segment calls, and no garbage collector. Still, it is giving the fearless concurrency environment. And now moving to the library-based concurrency. So there are so many ways to implement the concurrency in Rust. And in today's talk, I will go through the library-based concurrency. We can use some standard library in Rust, and we can implement the concurrency. So there are three ways to implement the concurrency in Rust. First is using threads to run the code simultaneously, and second is using message passing to transfer the data between threads, and third one is the shared state concurrency. So this is the example of the spawning a thread and to achieve the concurrency. So here we are spawning a child thread along with the main thread, and we are assigning multiple tasks in a single child thread. Here you can see that we implemented a loop. It will start from 1 to 5, and it will print that value as well. And it will also wait for the and main thread will also wait for the child thread to implement completely. And in output you will see it will print completely. In this left side example, you will see the potential of the standard thread library, where it is the actual example of the data races. So when we create a vector in a main thread, and when we spawn a thread, the child thread, and the key thing here is the move keyword. So it actually take the advantage of the ownership concept, and it transfers the ownership to the child thread, and then we can modify or push the data into a child thread. And and if we want to modify or push the data into a main thread, we can't do it because it may leads to the condition of the data races. But so to avoid that situation, Rust compiler at compile time gives the error. And in the right side example, when we create a vector by using the concept of borrowing, we are just only giving the references. But here the problem is that um, it is actually also going to give an error, because here the borrowing will comes with the lifetimes. So the one condition can also arise here, that main function can return before the actual child thread starts. So it can also give the error of that value doesn't live long enough. So if we want to share the data like the vector 1, 2, 3 between main thread as well as child thread, then we can use the reference count type, RC type. So RC is a technique where we generally store the number of references or pointers. So here, even though we have implemented the ownership, that we also use the move keyword, but still we cannot implement or we cannot run this code, because the Rust compiler infer this situation, and it tells that this RC T type we cannot share across the threads, because it is not the safely move. So at the in the static analysis, it gives that error as well, and it is also not atomic in nature. So the standard library sync are we can achieve this thing. We can share the data between main thread as well as child thread, and we can use the reference count as well with atomicity. And here you can see this example. So in child thread itself, we can print the vector, as well as we can also transfer the references to the main thread as well, and we can also print the both vector in child as well as in main thread as well. The second thing that I explained you, that we can also implement the concurrency via message passing. So to achieve the message sending concurrency, Rust standard library provides an implementation of channels. So channel, what is the channel? Channel is nothing but it is the pipeline where one single thread can pass the message to the another thread. And in the right side, you can see one example of the same thing. Here we use the MPSC crate, and we spawn one thread, and in that thread we are creating a thread, and with the message connected, and we are transferring that message to the main thread from the child thread. And in the main thread, we are receiving that message, and we are printing the Toyota connected here. So it is the example where we are sending the connected string from the child thread and we are receiving that thing in a main thread, and it gives the thread isolation as well. And the third thing, we can achieve the concurrency via shared state. So in shared state, what we do generally, there are multiple threads that can access the same memory location at the same time, but we use the concept of the mutex, that is the mutual exclusion. So at a time, one thread can can access shared state at a time. So in this example, we create a mutex, you can see here, and we wrap around the arc object, and then we are creating a multiple threads. So in this example, we created around 16 threads, and all the threads going to use the mutex, and we also created a atomic copy of the shared state, and all the threads one by one will access this shared state here, and they will lock this shared state, and then they will access it, and then the another thread will come and it will access the shared state, but in a mutex format. And then it is ensuring that we can multiple threads can also access the same thread to reduce the memory usage. And the another library in Rust that we have, that is the Rayon. It is the lightweight external crate or library. Using it, we can achieve the concurrency via parallelism, and it generally converts the sequential computation into a parallel computations. And Rayon has one good characteristic, that it automatically spawn the threads, and it actually spawn the thread as per the logical CPU available at the system, or otherwise it takes the physical CPU available at the system, and it spawned accordingly. In the right side, it is the example of it. In the above side, you can see it is just standard code, where it is of the sum of squares. But when we use the Rayon library, it is just about we change the iterator into the parallel iterator, and we can implement or achieve the concurrency. Here, I'm also going to show one live example of the same. So in this example, you will see that first I will run a program which will work on the basis of the sequential computation, and then I will show one example where I will use the Rayon library, and it will use the parallel computation, and it will show the output. And in this example, I'm going to calculate the factorial of 50,000. So I will first run without Rayon. So it takes around some 10 to 12 seconds. It will calculate the factorial of 50,000, and you will see how big the value it is, the factorial 50,000. Here is the output. So this is the value of the factorial 50,000, and it took around 14.18 seconds to compute the factorial of 50,000. So the same example, if we use the Rayon library, and by using the parallel computation, you will see by using the concurrency how much we can reduce this time. So I'm going to show that thing as well. See, the same factorial 50,000 using the Rayon library and the concurrency, it took around 3.35 seconds. So it is 1/4 of the previous implementation, previous time. And I also want to show you how we can write this thing in VS Code, just a brief. So now we just need to change we just need to add some dependency in cargo toml file, that is the rayon library, and we also include the num4 because we are dealing with a very big number, unassigned integer, and here we use that library, and then we write the function to calculate the factorial, and here we are trying to achieve using the rayon. That's why we are using the parallel iterator method as well. And in main function, we are initialized with the time that, and we are trying to calculate how much time it is taking when we are trying to calculate the factorial of 50,000, and then we are showing that time as well. So you can see that using concurrency, how powerful it is and how it is simple in Rust as well. That's all about from my side. Any questions?
We are
Yes.
receiving questions for Mohit. So anyone interested to ask any questions in the chat or to one of our organizers, please feel free to.
So Nanda is asking something. Can you please let know the memory space to run? Okay, so Nanda, I think you are asking when I run this live example code, right?
Nanda, your mic is unmuted. You can ask your question.
So Nanda, related to the memory space, it is not going to take the lot of memory because it is lightweight crate. So Rust itself optimize this thing for you, and it takes lesser memory when it trying to execute for you. Yes, Karthik, I have used Crossbeam create as well, but in this talk, I have not included the Crossbeam. There are so many external create that are available in Rust. Using those create, we can achieve the concurrency, and Rayon is the one of the example of it. There are a lot of things or lot of external create is available in Rust, and if you want to, depending on the use cases, we can use different create as well, different library as well, and those libraries also available in the documentation. If you want to see, the complete documentation is available in the Rust community, in Rust documentation as well. Okay, so in TCN we are going to use the Rust in production as well, and the kind of issue that we faced, I think our one of the senior that Eric can give you more insight about you when what kind of issue we generally face this thing.
Yeah, so I mean, using Rust in production, I mean, it's no different than any other language, especially a compiled language. If you've ever used Go or anything, it's very similar to that. I mean, it's very lightweight when you're using web services and stuff like that. I wouldn't say there's too many issues outside of long compile times during the releases and stuff. Release builds could take a while to compile from fresh, but outside of that, I mean, it's got great tracing and logging libraries. It plugs into open telemetry. It's got Datadog plugins. It's supported by Amazon and Google. They're the biggest employers of Rust employees in the world. Cloudflare uses it, so Rust can handle trillions of requests a day, basically. Every web request basically goes through Cloudflare, which in turn uses Rust. So there are several companies using it in production. All of Toyota Connected will be using Rust in production in the next year or two, and I mean, I don't foresee any weird issues popping up.
Great. We'll wait for probably a couple of more minutes to invite any more questions, and then can go to the next session. There's one more question out there. SQLX or Diesel or over. Would anyone like to take the question?
So, Karthik, could you please explain what do you want to ask?
Karthik, your mic is unmuted. You can elaborate your question.
What is the preferred way to connect to databases? So I think depending on the kind of project or the kind of use cases, it depends. So Sandhya is asking something. Okay. How do I strip? How device driver should be written to handle concurrency in Rust? So Sandhya, generally when we write the device driver, we do the implementation using async IO, and sometimes we use some other external library as well. And I think Arik has more experience on it, so I think Arik can answer this question as well.
Yeah, so recently Rust was merged into the Linux kernel, like last week actually, and there was a team that has already written the Apple M1 Silicon GPU drivers, so you could dual boot Linux on an Apple M1. And basically, you use IOU ring, which is the async implementation in Linux, and there are some libraries you can use to do that. Or you can just use async, but I would advise to use IOU ring since that's the Linux way of doing async after like Linux 5.3. But there are live streams of them actually writing that GPU kernel you can find on YouTube, and it's super interesting. And right now there's not a lot of big device drivers, but that Apple M1 GPU was like the first step towards that. And I do know NVIDIA does offer Rust bindings to certain things now, and it is a very active spot in the Rust space trying to get CUDA working in Rust. So there's a lot of interesting things like that happening. But for any device driver thing, I mean, if you're on a Linux machine, or if you're working on the Linux kernel or whatever, you're trying to write a driver, you should be using IO ring or the Linux way of doing that, right?
Cool. So I think you guys can have your questions noted somewhere and can also send it to the organizers, one of the organizers or the organization email. So I would like to start with the next session. So we have been carrying forward with an experiment wherein we wanted to see, how many people are, kind of up for a challenge, or more like how many people are open to using Rust as one of their experimental endeavors, and we kind of wanted to try out a coding contest, and then we put out a bunch of questions out a couple of weeks back, and then we got numerous responses from a lot of enthusiastic engineers implementing various solutions to the problems. And out of a lot, we were able to curate and take a few solutions, and out of that, we kind of select one winner. The winner is Roland for Code Crunch contest. And this session is going to be something like, we're going to invite Roland to discuss about his solution, like how he approached the problem, what does he think about developing in Rust in that course of time. And then we're going to listen to Roland for the next 15-20 minutes on his solutions. So I give the stage to Roland, and I think one of the organizers can help Roland present his solution. Can we unmute Roland?
Hey, am I audible?
Great. Cool.
Hey, yeah. To give a little bit background about myself, I am Roland Chauvin, and I work with an organization which maintains an open source project called a Safe Network, which is a peer-to-peer file storage network, kind of similar to IPFS. If you heard about it, IPFS is similarly built on top of BitTorrent protocol. So I'll start. Can you please open the PDF, which is in the GitHub repo? Yep. So I'll center the talk around Rust libraries that I use to solve the code crunch, and also follow through the answers. So one of the questions that was asked in the contest was given a location and a place of interest, for example, a restaurant or a gas station or something. One should return the total number of places around that location, also the places which are currently open. So to solve these kind of questions, it's kind of useful to write a simple application, and CLI applications are the most simplest, but they have one major pitfall, is that you have to parse the user arguments, and as you all know, user arguments can be really totally random, and it can crash your program if you're trying to parse something into a different type. So that's where clap comes in. Clap is a command line argument parser. So it basically does what it says. So we can we can use builder pattern, which I think Eric will go upon in the next session, to get the arguments. So it's easy as calling a couple of functions with the argument that you want, the default value provided, and how you should parse it. For example, here we are parsing the latitude as a f64, which is floating point. And we can also, after getting all the arguments, we can get whatever argument we want one by one. Can you go to the next slide? Yeah. So that's one way to do it. But if your application is very large, that's not really a good way to build it. So that's why we have derive macros. So as you can see in first line, we have derive parser. So parser is a trait in Rust.
Roland, I'm really sorry, just to stop you right there. Can you explain a little bit about the problem statement that you took, and then probably get to this information so that the audience kind of know like what is really happening?
So can I go to the previous slide? Yeah. So this at this point, I will be taking the user inputs. For example, since I want the latitude, longitude, and as well as the keyword to search for, I'll be using this clap library to get all the input from the user. So after getting all the input from the user, so the thing is, we are gonna use the Google Map API endpoint to get all the details that we need. For example, given a location, we need all the restaurants around that location. So we'll be using Google's API for it. So after using the Google's API, we will have to parse whatever we get response from the API into a struct in Rust for us to be processed. So we'll be using a different library for that as well. So as the initial point to get the user inputs, we will use the clap library. So this is basically a different way to get the user inputs. So this is a much cleaner and a much more organized way to do it. Can you go to the next one? And so that's the first part of the program, that is getting the user inputs. And a clap can do even more than that. It can have shell completions. It can have suggested fixes for users as well. Now that we have the user input, the next step is to send the contact the Google Maps API endpoint. For that, we need a HTTP client to do it, and request with a W in it is a library that we can use to make HTTP requests. So it's spelled that way for easy searching in the internet. So yeah. So as we can see, we will provide in the URL, which will contain all the information that we got from the previous part from the user. For example, the location, the string that we need to search for, everything. Then we will get that URL. As we can see, we can use request, get, and URL. And after getting the response, we can check for the status of the response. If it is okay, we will do something with it. If it is unauthorized, we haven't provided a Google Developer API key to it. If it's an error, we will send the error back to the caller of this function. So in this, as we actually request is an async HTTP client, which can do concurrent requests as we concurrent request. But the thing is here, we will be doing sequential request, because the thing about Google API is that Google API sends out 20 results and also sends a next page token. So you kind of have to make and the limit is like 60 outputs. And so after you get the first request, a response, you can get the next page token from it, and we have to use that to get the next page of it, obviously. So it's like there is no way to concurrently do it. We have to go sequentially. So even though we use the async and await keyword, it's sequential in nature. Can you go to the next one? So after we get the response, the response is in JSON format, and we need to somehow parse the response into a struct we can then use in Rust. So that's where SERD comes in. SERD is the most popular serialization and deserialization library, which allows you to go from a Rust struct into a JSON or a YAML or whatever binary format or whatever format you want, and vice versa. That is, you can go back from JSON back to, you can do whatever you want. So it's really easy to implement. All you have to do is, as you can see in the first line, we have to call derive, serialize, and deserialize. So derive is a macro in Rust, which what it does is it basically implements serialize and deserialize traits for our structs. So traits are similar to interfaces in Java. So yeah. So if you can see in the previous slide, we can see that if the status code is okay, we are taking the response, converting into a JSON, and parsing it using nearby places parser. So the nearby places parser, as you can see from the next slide, so the JSON response that we get will be parsed into this format. So, and as you can see, we have, and the JSON can have nested objects. So for each object, we should create another struct to store it and parse it. And one good thing about SERDI is that if the JSON contains extra, fields or objects that we don't understand, that we haven't described here, it will be automatically ignored, and we will not get an error. So it's really easy to filter out whatever stuffs that you need. So now that we have the response from the Google API server, now, can you go to the next slide? We will just pass it to some functions to get all the details that we want. That is the total places that we got and the places which are open. And we now have to have we have to display it to the user somehow. And we can normally use print statements to display it, but we have some really cool third-party libraries for it, which, for in this case, we have CLI table, which prints the results as a table. So in this library, it expects the user to provide each row as a vector. So as we can see, we have a vector. We, after the map statement, yeah, exactly there. So we have 3 items in the vector. So that constitutes an entire row. And we'll collect all the rows into a vector, provide some title to the table, and we'll print the table, and we can see the output in the next page. So this is the solution to the first problem, that given the latitude, longitude, and the search statement, a search text, we will fetch the Google API and return the number of places within 1 kilometer radius from the location. So there are 45 places which are currently there. So it's the location is actually Chennai. So it's too densely populated, and there are a lot of restaurants in within 2 kilometer area, and I reached the limit of 60 results that I got from Google Map API. Probably we can improve upon this, to make multiple requests, by changing the location bit by bit. But yeah, this is the solution that I wrote. So we have 45 places that are 1 kilometer away from that location that we gave. Yeah, can you go to the next slide? So if you can open my solutions, can you go to source? Words, the last one. Main.rs. So this is another question that was asked in the code contest. And so this is a really simple one. So given a word, any random word, we have to find all the permutations of the word and find all the words which are valid. So it follows the same pattern. To get the user word from the user, we'll be using the clap library to get the arguments. And after that, we will use a dictionary API to call the server, and it will basically we'll send the word to the server, and we will check if the word is valid or not. And if the word is valid, we will return the valid word. Just it's done in this way because this is run concurrently. So yeah, I'll go through the code. So as we can see, we will get the permutations of the word very easily in Rust just by calling .permutations method. This is provided by a library called as iter-tools. It just solves the problem for us. So yeah, for each word, what we do is we use a library called as Tokyo. So if you can go into the slide. So Tokyo is a asynchronous runtime. Consider other languages which uses async. The most common language that comes to my mind is JavaScript. And to run async code in that, we use Node.js. And Node.js has a built-in runtime with it, asynchronous runtime. So it is the thing which drives the async code that you write. But in Rust, we have the async and await keyword, but the language does not come with a built-in runtime with it. Instead, Rust team just gave it to the third-party implementators to implement whatever runtime they want. And Tokyo is one of those runtime, which is the most popular one. So we can use Tokyo if the program is actually needs to wait for something. It can be waiting for IO. For example, you can reading something from your disk or sending a request to a network. So for these kind of things, you can use Tokyo. And so this will what Tokyo does is that it will spawn something called as tasks. These are completely different from threads in traditional sense. As in, tasks are really cheaper to spawn. You can spawn like thousands of tasks, but it is efficient because if you were to spawn an actual thread, you have to do a system call. You will have to tell your operating system that you want a new thread, and it will do a lot of overhead stuff to give you that thread. But in this case, tasks are really lightweight, and these are handled by Tokyo, so you don't have to care. You can spawn as much tasks as you want. And the thing about Tokyo is that it is concurrent and as well as parallel. You can think about it this way: if you have a single thread can have multiple tasks as well, and you can switch between task 1, task 2, and again task 1. So this, you are basically achieving concurrency with this. And also it can do parallel. That is, if we have multiple actual system threads. Now, as we saw from the first slide in the first session, you can think them of like, two lines running parallelly, and you can have lot of tasks intermingled in them. So you can do concurrency as well as parallelism with Tokyo. So to just call Tokyo runtime, it's really easy. As we can see from the code below, all you have to do is call this macro, and it will populate the code with the runtime. You don't have to worry about it. We can customize it as much as we want if you can read the Tokyo documentations. If you can go to the next slide, we'll see how we can use Tokyo to solve our problem. So as you can see, in line number 4, we are getting the permutation of that word. It's a single permutation. Now we have to check if that word is correct or not. So for this, so if you can think about it, a word which is 5 characters long will have 120 permutations. So doing 120 calls to a server and waiting for each one at a time is not really feasible. So this is where Tokyo can shine. So what we will do is spawn Tokyo tasks. It will give us a handle. As we can see, isValid is the function that we saw in the, so it basically makes a call to the API. There is nothing more to it. And we'll get a handle back, and we will await on those handle in the next for loop. And this will basically run all the tasks in concurrent and in parallel. So you can make those 120 requests in probably 6 seconds. So it will probably take 6 seconds to execute this problem and give you back the solution instead of waiting for like 10 minutes or something. So yeah, can you go to the next one? So that's how that problem is solved. You can, so crates.io is the official package manage, third-party library website for Rust. You can go there to explore a lot of different trades, all the third-party trades, and it's quite fun. Yeah, that's it for me. Thank you.
That was indeed a very tight and very precise presentation, and congrats, Roland, for winning the contest, and we will soon be sending you the goodies. And this and one more thing, the contest is, even though kind of ended with this Techceleration event, we are still inviting people to send their submissions along, and we will keep reviewing it. We have reviewers in the organization who can review the code, give you the comments, and if something is really good, we will have something special for you. We will mention your name in our post. Probably if it qualifies to be one of the top submissions, we can send you goodies. So we are still inviting more people to send the submissions, people who are here who are interested to but have not. And in the meantime, if you guys have a chance, you can visit our meetup group. We are close to 900 members strong, and we will keep on having more innovative events and more contests posted there. And also do please follow us on LinkedIn and Twitter as well. So right now, circling back to the event, now we have a very special person presenting about Rust, and even though I have not worked directly with him or under him, I've known his name all along in the organization. He has been a strong proponent of Rust. He has been in numerous Rust-based organizations, like open source organizations. Have been hearing out his names and presentations all along. So I'm now handing over the stage to Eric McBride, our own Rust expert, here to talk about builder patterns, interop in Rust, and more. So over to you, Eric.
Hey, thanks. I appreciate all the kind words. I definitely don't view myself that way, but so let me share my screen here. All right. So today we are going to talk about FFI code. That is foreign function interface code, and how to write idiomatic unsafe code. A lot of people are scared of unsafe code and interoping into C, and it's a very dense subject matter, and I've kind of broke it down into a very easy to follow thing to do. So a little about me. I've been an engineer at Toyota Connected North America for around 4.5 years. I graduated college about 11 years ago, so I've been in the industry as a professional for around 11 years. I've been writing Rust full time for 3.5 years, and I've been writing Rust off and on since about 2016. I live in the country with my wife and daughter. I have 4 dogs, so my wife and daughter are asleep right now, so if my dogs start freaking out, I'll apologize in advance. I got a couple of cats, and we have several chickens, and there's a link to my GitHub. So just a general overview. I'm just going to do an introduction and show some examples of the builder pattern and a couple of different design patterns there are for that. Then I'll give a high-level overview of FFI. Then I'll give a sample application overview discussing what we're going to see in the code. And after that, I'll talk about combining the builder pattern plus FFI. Then I will talk about maybe an init and out pointers. Then I'll have a little Q&A session afterwards. So the builder pattern. What is the builder pattern? The builder pattern allows construction of a highly configurable or complex object in Rust. The builder pattern is seen more in Rust than other languages due to the lack of overloading, meaning method overloading. There's no inheritance or anything really in Rust, so you can't overload other methods. But what you can do is you can wrap method or function calls in other functions and chain them together with other calls. And that's kind of what it means. So you see this pattern a little more than you would, say, in C# or Java or something like that. In Rust, there are 2 types of builders. There's a consuming builder, means it consumes the object and you have to rebind the value every time. and a non-consuming builder, which is the preferred builder type, meaning that you can keep mutating it in place and you don't have to rebind the object to another variable. Usually use a non-consuming builder for more complex configuration types due to the borrowing that happens, meaning if you have a conditional statement, you can do like foo equals bar dot. I'm not even going to explain this. I'll show you code on the next page. I'm sorry. And if you consume your builder, you will have to reassign the value instead of just mutating it in place. An example of something that consumes a builder is the threading library, because you call dot spawn at the end and it just consumes that thread. So in the previous presentation, they talked about the builder pattern using command, and that is like the de facto non-consuming example. So if you look here, we have an output for, if it's Windows, you know, you got to do /c echo hello, because Windows uses cmd.exe, which is completely different from the Unix bash or shell, right? So if you look here, you can see it's just chained together. That's what the builder pattern is like you create a new object, then you can chain methods to it that are optional. And down here you can see that they're binding the standard output of this to hello. Oh, I think it skipped something here. I'm sorry. Yeah, for some reason it skipped. Oh my goodness, I'm sorry. I'm not sure why it's skipping that. Anyway, we'll look right here. So this is a consuming example. And by what I mean by that is, if you look down here, you can see where they're having to rebind thread to the variable every time they build onto it, meaning they can't just do thread.named and it will mutate it in place. You have to rebind it to a variable. And you can see where that would get kind of annoying if you had a bunch of conditionals like this one down here, because you couldn't just mutate in place. You have to keep rebinding and rebinding. Let me start my slideshow back up. Okay, so FFI real fast at a high level. It allows for Rust to C interrupt and C to Rust interrupt. It also does other things like C++. There's other ABIs in Rust for that. An extern keyword will let you select a C ABI. By default, we don't see it visually, but all functions in Rust are extern Rust, because and that just means it's using the Rust ABI. It informs the compiler that the extern function will be called by a different language. BindGen, which is what I'm going to use for my demo, allows for an easy generation of C to Rust bindings. This will generate code based off a build script and C headers and shared objects. So you don't have to handwrite the bridges. Without BindGen, you would actually have to use the link. There's a link macro, and you would have to link to the shared object manually, and you would have to actually write a bunch of code that's not fun to write. And calls to FFI functions are unsafe by nature due to C controlling the underlying function calls. Rust can't guarantee all of its guarantees in C just due to C controlling the underlying functions. Unsafe. Unsafe in Rust has a bad rap. You should definitely minimize the usage of the unsafe keyword, but unsafe only allows you to do the following, which they're literally always doable in any C or C++ code, and there's billions of lines of that running in production, right? So if you have a little section where you have to use unsafe, it's not the end of the world. It doesn't mean your program's going to blow up, right? So all it allows you to do is to dereference a raw pointer, call an unsafe function or method, which would be FFI code, right? Access or modify a mutable static variable. That is bad because it's basically global state at that point, and global state's always a bad thing in Rust. You really don't want that unless you're using something like atomics. It allows you to implement an unsafe trait. An unsafe trait could be an interface from C++, for example. Access fields of unions. Rust does have a union type, but since it's an untagged union, it's not safe just due to how untagged unions work. And we'll be using the unsafe keyword only in my demo for calling FFI functions. All right, so the sample application is going to be an employee mainframe or in-house server. So we have an old proven employee record mainframe application written in C. Over the past 3 decades, it's done its job, but we want to get rid of our mainframe or server and move it to the cloud. We also want to be able to reuse the old code while being able to extend it, and we want to use Rust because we want to leverage their awesome libraries, right? And we will use FFI to reuse the old server code. We use simple methods so we can understand dense concepts in this. Please just note that this is just for demo purposes, and I probably would not actually write my code one-to-one with how this is for a real application, because what I end up doing is I show the builder pattern in a real simple way so you can digest it. And same thing with the FFI bindings. Like, I'm not doing anything too complex because I wanted this to be beginner friendly as well. And continuing on with that, a lot of the CSDKs and APIs want you to create pointers and pass them to populate a config value or to get a default value. And you pass into a function and the function will populate a pointer, then you register it with some other function call or component, right? This is very, in my experience, I've done this a lot with like config values and stuff. You pass in an uninitialized pointer and they will populate it for you for default values, or you can pass in a populated pointer and they'll do the same, like they'll just send it back to you. In the Rustnomicon, in the maybe on a net section, they're referred to as out pointers. In C doc strings, you'll often see it as at param out, then you'll see out param in as well, just like signifying that you're sending it in and it's populating the pointer and sending it out, basically. Rust used to provide a uninitialized type for these kind of situations, but it was a big foot gun. And this is a quote from the standard library, actually. It says the reason for deprecation is that the function basically cannot be used correctly. It has the same effect as maybe on init, assume init, which I'll talk about when I show the code. As the assume init documentation explains, the Rust compiler assumes that values are properly initialized. As a consequence, calling memory uninitialized on a bool causes immediate undefined behavior for returning a bool that is not definitely either true or false. Whereas truly uninitialized memory, like what gets returned here, is special in that the compiler knows what it does not have a fixed value. This makes it undefined behavior to have uninitialized data in a variable, even if the variable has an integer type. Notice that the rules around uninitialized integers are not finalized yet, but until they are, it is advisable to avoid them. Basically, what it's saying is that you could have uninitialized memory and you send it into a C function. And if it doesn't get populated, we're just taking C's word for it. What maybe uninit does is it gives you two states, uninit or init, and it puts the responsibility on the user that it's been initialized, meaning that you do a maybe uninit, then you call the C function and you pass that in as a mut pointer to populate it. Then you could call assume init on it, and that's because you know it's been initialized. And it's hard. This is dense, and I will show you what I mean when we get to the code. So now I'm going to go to my IDE over here, and I will try to make this bigger. Okay, so just to start off, this is what a Rust project looks like. There's a source folder, there's a cargo toml. I'm going to open up the cargo toml. If you're not familiar with what cargo it is, it's a dependency manager. Here in the build dependencies, you can see I have bindgen, which is going to generate our code for us, our C to Rust code. I have an example, which is what's on the right-hand side of the screen. It's going to be showing the builder pattern and me calling the library over there. Then dependencies, I use these 3 dependencies in almost everything. Anyhow is an awesome application level error generator. You use it when you just kind of want to log and forget errors and you really don't have to handle them, which happens a lot in application code. I use Strum for absolutely everything. I'm a big fan of algebraic data types, and Rust has excellent enums. And Strum just gives you a lot of cool macros out of the box, and I use them in here. I'm a huge fan of enums. So let's look at this mainframe code we're going to be reusing. It's really some dense stuff here. So I'm going to open up my employee.c file, as we can see here, we have some functions. I have a set employee name, a set employee address, a set default 401k. If you're not familiar with what a 401k is, it's like a retirement plan. But basically, I did this on purpose, but basically set employee name in the mainframe, if this was a real application, it'd be writing to a database or using some logic with the employee name and enriching the employee name. Same thing with the address. You'd be registering it, and you would be like registering it with the database. And the set default 401k is an example of an out pointer where I send in a default value and I expect to get something back, right? So what Rust needs to generate bindings is it needs a shared object, which you see here, the employee.so, and it needs a header file. By default and by idiom, bindgen wants you to use a wrapper.h. So if I open this up, you can see I'm including an employee.h, and I open that up. And you can see here I have this enum of error types, or employee status is basically what it is. And I just have the function names in there. So if I go here, there is this build.rs script. What is this? I open it up, and in Rust, if there's a build.rs script, before the compile of the program happens, it actually runs this. So basically what I'm doing here is these first two lines is I am telling it it's where to look for the shared object, basically. The second line, it's the full path to it, right? I have an employee folder and opt. Then here you'll see I'm linking to the dynamic library employee. Here I have a bindings, which is basically I'm using bindgen to look in this header right here and generate bindings. Then I have an out path, which is where the bindings are going to be generated to. Then I write the bindings to a file. So if I open up my target directory, debug, build, open up employee FFI, sorry, wrong one. It generates two. So here's the out folder and here's the bindings. So this generates the C to Rust bindings for me. So these are the FFI functions I can call. If you look here, I have these three constants. This is from the enum that I declared in the header file for error types. Depending on your architecture, it will generate a different type, like U32 here. On ARM, it might be U64, for example. And Rust has a way to combat that, and that's what you're seeing here with the standard OS raw C char or C int. I really don't have a example here where it would be different, but they do have like a CU long and a C long, which means if something on Ubuntu, on x86 Ubuntu took a U32, it might take a U64 on ARM. So you would just use the OS raw CU long in your Rust code instead of hard coding U32 or U64, because you might see failures on the ARM machine versus the x86 machine. So we just have these three functions here that have been generated for us. So if we go into the source code, I have this lib.rs, we open it up. A mod in Rust, it's similar to, it's just a library within there, right? Within a Rust crate. It's a module. So what ends up happening is I have a public module there. I open up FFI, and here I have a type alias for error, and it just points at anyhow error. Here I have a mod called bindings, and this is actually where I include the bindings that were generated, which I just showed. Then I like to remap those constants to an enum, especially with errors, right? And what happens here is you can have repr types in Rust. A lot of it has to do with memory alignment in C, but you can also repr primitives. And what this will allow you to do is, like, if it returns 0, that we know it's okay, right? If it returns 0 from the C code. So what this will allow you to do something cool like the following down here, where I can do employee errors from repr. And instead of a 0 being printed out for the error, it'd be, or 0 is not going to be an arrow, but instead of invalid argument being a 0, it'd actually say invalid argument. So that's what the from repper does as part of Strum, and it's super cool. And I also use it down here for the stipend type, or for the retirement info, for the out pointer. So what we're going to look at it today is, say you get a payload in on your cloud request to update an employee record, right? So we have a name and address that we record to a database. Then someone went in and added retirement info after the fact in our mainframe, and they decided to use a pointer to populate a default field. So that's where maybe on init will come into place. Then they wanted a new feature since we made it in Rust, and that's where the office stipend is. So you could call it, here's a new function. It's just a constructor. You pass in a name, address, retirement info, office stipend. I will demo all this on the right here in a second. So I decided to use the non-consuming builder pattern. And that way I don't have to rebind anything. And what's going on here is there's lifetimes involved, because there has to be, because you're borrowing. Every method call you're borrowing, and you don't want to consume anything. So I don't like marking lifetimes with A's, really. I really think that's kind of confusing, especially if you get in deep. So basically what I like to do is name what it has to outlive, right? So in this case, it has to outlive self or employee. I didn't do self because I didn't want it to be redundant. So I chose the lifetime name to be employee. So basically what I'm telling each one of these methods is that this can only be called as long as employee is not dropped, as long as the original value isn't dropped. So this allows you to mutate it in place and not consume it as we're doing the chain builder. And you'll see that on every one of there. It's very, you can wrap it in result. And lifetimes are a dense thing. It takes quite a while to get. Basically, you have to tell the compiler that you guarantee that you're not going to drop employee or self. And if you do, you can't use these functions. So the functions are pretty simple. We have change employee name, which is just going to rebind a new name to self. We have record employee name, which we'll call our FFI code. Here you can see I'm having to convert a Rust string to a C string. I'm getting a response back from set employee name. And if the response does not equal 0, 0 in our case is okay, because we return 0 from the C code. We'll return an anyhow error. Then if it succeeds, we'll see successfully saved employee name to database. Then we return self. We got to return self each time. That's how we're able to chain the builder pattern together. Change employee address is the same as change employee name. We just rebind address to self. Record employee address, same thing. We create a C string. We call the C function right underneath it. Then if it's not 0, there's an error. If it succeeds, we print. Then there's set retirement type. This is kind of where it changes. So, you know, the person that wrote the C code, you know, they did something weird. You know, of course, we all write perfect code and we don't do weird things, right? For some reason, if there was no retirement info, they defaulted to the default 401k type instead of none. So here I'm checking to see if the retirement info is none. And if it is, we create this maybe an init type. So what this is doing is we're feeding it uninitialized memory, and we want the C code to populate our default, right? So if you look here, I just do this retirement type. It's a maybe uninit of C int type, because that's the type that's returned from the function. So if we look here, I have a let rest equal unsafe binding set default 401k. Then I have a retirement type dot asmut pointer. Asmut pointer means it's a mutable pointer, and in Rust, it's basically turning this into a mut C int type, meaning it's mutable, meaning that the C code can change it. If it was just as pointer, it'd be a const C int, meaning it cannot be changed. It's immutable. It's read only. So what ends up happening is with maybe on a init, there's a lot of times in C code where you have to just keep passing in pointers as you populate different values for it. and you can keep maybe on a init, like you could keep this type wrapped in a struct and keep doing that until you want the final value. Then you will call assume init, like I do down here. So I check to see if there's an error, and if there's not an error, I set retirement info to the value we got populated from that C code by calling assume init. I know that I passed in that type right here as a nut pointer. There was no error, so I'm assuming that it's been initialized. That's kind of the gist of it. Then I return self, and if retirement info is already populated, we just return self because we don't need to set anything, right? Then we have this new function called use office stipend. And basically, we're just seeing if they've spent $1,000. If it's between 999 and 0, it's partially used, else it's not used, right? Then we just set the value here. So I'm going to save this. I'm going to go back. I'm going to set the, if you're not familiar with LD library path or library path, basically what ends up happening is that header file I showed y'all earlier in wrapper.h. The Rust code is generated from that, but it's got a link to a shared object to be able to actually call into it. And that's what this code right here is doing. So if we look over at the right-hand side, my example is employee. So basically, I'm just creating an empty or a new employee type right here of Eric McBride. I live on 1234 Toyota Street. I have no retirement info, and I have no office stipend. So I'm going to run this, and it should just print out that basic info right there. As you can see down here, it did just that. It just printed out what I needed. Say we get a payload in, and I legally changed my name to Derek McBride, and I want to set my retirement type in the database, right? So I want to change to a default 401k instead of the none status. So what I do here is I do .change employee name, which will rebind my name to a new variable. The record employee name will save it in the database, and set retirement type will set my new retirement type, which you can see I'm passing in nothing, but it will set it to the default using that out pointer. So I will run it again. And down here, you can see now my name's Derek McBride. I live on 1234 Toyota Street. I have a default 401k, and I haven't done anything with my office stipend yet. So let's say I moved. Derek McBride decides to move. So I'm going to change my address, which will rebound my address. Then I will record it to a database. And as we can see down here, my name is still Derek McBride, but I've changed my address to 4321 Lexus Drive. Well, let's decide I moved back to my original house. I hate the name Derek. I like Eric. Then I decide to use $98 on my office stipend to buy a couple books, right? So now we're able to run all this. We can see all my changes. And down here, you can see I'm back to Eric McBride. I'm at 1234 Toyota Drive. I have a default 401k, and I've partially used my office stipend. So that's the end of my demo. And keep in mind, like if I was actually doing this, I wouldn't be doing change employee name and record employee name, right? I would do change employee name and I would write to the database. The reason I do this is because I feel like it's very easy visually to see what the builder pattern can do and how you can chain things together, especially based off of a payload or different endpoints or resource endpoints. It's easy to chain things together, or you can even have like a mid struct that's a configuration type. So you can call all the chains in a row, and if values are none, then you don't have to worry about anything, right? Just passing the payload in and out. That's all I really have demo and talk wise. I will take questions now. I know this was really dense, but I tried to break it down as easily as I could. So if y'all want to start questions, I'll be more than happy to answer questions. No questions?
Do we have any questions for Eric, guys? Probably. Otherwise, we'll wait for a couple of minutes and then we will go to the closing now. I'll wait for a minute, and if you guys have any questions, you have a minute to put it out into the chat. We got a question. Nanda asked smallest size of the application that can be used on Rust.
I mean, just like, bytes, a couple bytes. If you have no dependencies or anything, you just got to link the standard library and print out hello world. I mean, on average, we have huge repos and a lot of dependencies, and our release binary would be 12 meg, 15 meg, and it'd be huge. Our ML models are much bigger in production and stuff like that. But I've never seen a Rust binary be too big, even with Tokyo runtime and stuff. It's all super small and compact.
Anything else, guys?
Yeah, so C++ code can be converted into Rust code. So it depends if the target's supported in Rust, but there's a library called CXX that allow you to manually write the bridges. Then Google has a project called AutoCXX that is very similar to BindGen. I do know there are a couple issues with templating. If you use templating in C++, it doesn't translate directly to Rust being generated, but you can manually do the bridge and get it to work. Then there's some issues with some of the dynamic dispatch stuff, but there's ways to fix that too. And that's just the bridge across. I mean, there is going to be differences, and you're probably going to have to hand roll stuff depending on how many modern methods and stuff are called in C++. And I wouldn't expect async C++ and like the newer stuff to work too well. So Rust on ARM. We're using Rust on ARM right now on a chipset. I can't talk too much about it, but I mean, the M1 Max compile really fast and much faster than the x86. And we haven't had any performance issues on ARM. It looks great. It's running fast, hardly any CPU usage or anything on the embedded chipset. How do you debug Rust code? I print line. I'm a printer, or I use tracing. But if I'm doing the C or C++ interop, I use valgrind. Like anytime I write a function, I will generate the binary and I'll run valgrind against it to make sure there's no memory links in the underlying C code. Because what ends up happening a lot is you trust the C developers or the C vendors to guard against seg faults and stuff, and a lot of them don't check for null pointers. So you'll just seg fault in your code or test. So I end up just running valgrind. I find it much easier to run valgrind than like GDB or something like that. But you can run GDB. You can run any LLVM tooling against Rust and it works. So you don't even have to change your flow from C or C++ to Rust because it's just a core dump, basically.
Okay, guys, I think any more questions you guys can send through and email to us. We do have our Techceleration official mail, and I think we got one other question.
I'm not sure. If you could generate C from C#, you could definitely do it. We've done Haskell to C to Rust. I'm not familiar with C# enough to give an answer on that, but I'm guessing there is a way for C# to interop with C. So if you could do that, I'm sure you can do it. There's Dart to Rust bindings. There's all kinds of stuff. So I'd be very shocked if you couldn't do C# to Rust somehow, even if there's some kind of middleware where you have to generate C# to C, because we've done Haskell to C to Rust, then we've done Dart to C to Rust. So I'd be very surprised if you couldn't do C#. Yeah, Rust has built-in doc strings. It's Markdown. It's super nice. It's super easy. It will generate with a cargo command. You just do cargo docs, and it will generate all the JavaScript and HTML for you. That's what you see on the official Rust guide. It's all generated from doc strings. It's built into the language. Static analysis. I mean, there's cargo format and cargo clippy. There's a lot of stuff like that. Then there's things like Miri, which will look at memory bugs and stuff that could possibly happen with unsafe code. So that's all built into the language. Like, you don't have to. It's very. The good thing about Rust is there's official tooling for everything from the language developers. So you don't get into these weird arguments like in Python or JavaScript, like what linter do I use, blah, blah, blah. Rust gives it to you, so you don't have an opinion on that matter. And if you make an opinion on that matter and start fighting with people over it, that's your fault, because there's standard guides to absolutely everything. And it's built into the cargo tool.
Cool. We can wrap up the question train now, because we do have an official mail that we have posted in the chat. Toyota-Techceleration@toyotaconnected.co.in. You guys can have your questions, doubts, any contest submissions, more contest submissions, and all that to this email. Any more suggestions can also be mailed. And we also have a feedback form. You guys can fill it out. It's going to take a couple of minutes or something. And coming back to the event, thanks a lot, Eric, for putting your time now. I think it's like early in the morning there, and we really appreciate your time and your enthusiasm and Rust that you just came here and gave a presentation for us. And myself, like, absolutely. And I got really interested in the FFIs because we do a lot of C++ in our team, and now we're kind of thinking, okay, is it worth to move to Rust at this point? But I mean, great talk, and guys, so we have come to the end of the event now, and we have got a great talk from our Rustic